morning, everyone. Thanks for coming for this talk. I am Ganesh Raju. I'm a technical lead for the big data team at Linaro. So this talk is going to have two sections. The first section, we are going to do a small demo, basically showing how a city can use its own data and utilize it for doing some machine learning and things like that. It's going to use ODPi, spec-based native Hadoop, Apache Spark, H2O, and sparkling water to do the demo. And then the second section will be more on the Hadoop and the big data benchmarks. Benchmarks for Hadoop, Spark, and anything to with the big data itself. So in the first section, it's a demo. Like I said, it's going to have ODPi-based Hadoop. ODPi is a standards body where you have different Hadoop distros and ISVs come together to standardize Hadoop. If you see today's Hadoop ecosystem, you have various distros available, and each distro, they package all these open source components, and there's a lot of them. And the problem is they don't have a proper standardization. Now, one distro goes with a particular version, and the same kind of a tool in a different distro could be a different version of it. So for an enterprise or for an end user, when they go with a particular distro, they get logged in. They may have problems if, say, if they want to upgrade any particular component of the big data, they get stuck with distro provided the package. So that's why ODPi is collaborating with companies like IBM, Pivotal, SAS, Infosys. So I think there are about 30 member companies working together to on a common goal to standardize Hadoop or any big data platform. And also, since you spend less time in testing and less time in the configurations and fixing things, it reduces cost and reduces the complexity for the enterprise, for the end users. What ODPi also provides is a cross-compatibility. What that means is every distro who wants to, who's part of ODPi, they can get certified from ODPi. So ODPi provides some test suites that they can run and they can certify. And what that provides for the end user enterprises, cross-compatibility. They can go with one distro. Later on, they want to switch and go switch to another distro, they can do that. So right now, ODPi has two tracks. It has a runtime track and the operations. In the runtime, you have the classic Hadoop components, Hadoop HDFS, MapReduce, and Yarn. On the operations, right now we are looking at Apache Ambari. We are working on version 2 of the ODPi spec, and it is in the alpha stage, and it will be releasing pretty soon. Linaro is obviously a member of ODPi, and I am personally a member of the technical steering committee for that. So for this demo, we will be using native Hadoop version 2.7, that following the ODPi specifications. And we'll also use Apache Spark. Apache Spark is an in-memory processing, data processing engine. It provides development APIs for doing SQL workloads on big data, also streaming APIs for big data. And it also has machine learning algorithms built into it. The Spark was actually created as an alternative for Hadoop MapReduce, because MapReduce was a batch processing and it was pretty slow. So they wanted to bring in interactive processing, and that's the main goal of Apache Spark, is to provide a fast and interactive processing. And you can use Java, Scala, or Python for coding in Spark. So this demo will also use Spark that would be running on top of ODPi-based Hadoop, and it will use Hadoop's Yarn as the resource manager. So we will have a cluster of 3 nodes for this demo, and we'll have Spark running on top of ODPi. And then we'll also use H2O sparkling water, which will be running on top of Spark. H2O is again an in-memory, user-friendly machine learning API. It is compatible with Hadoop. It can run standalone, or it can run on top of Spark. The reason that we are using H2O sparkling water on top of Spark is very good in fast interactive data processing. And H2O is provides a very user-friendly machine learning APIs. And both Spark and H2O, they work well integrated. Spark has this concept of RDDs and data frames to have the data in their memory, and H2O has something called H2O frame. So you can load data into Spark's RDDs or data frame and then move it to H2O frame, and you can even load it to H2O frame and bring it back to RDDs. One caveat is H2O uses the same memory of the Spark and the same executors. So if you are loading your data into a Spark's RDD or a data frame and then converting into a H2O frame, there is no penalty. But if you're doing the other way around, if you're having H2O frame, the data loaded into H2O frame, and you want to convert into a Spark, there's a copy that is made of the memory, so you may have a little bit penalty hit. H2O comes with a visualization UI, a web UI. It's called H2O Flow. Basically, that's a very user-friendly way for you to choose various machine learning algorithms, and easy way for you to build models on the data, and then you can apply the machine learning algorithms and do predictive analysis. So with that, we'll get into the demo. Again, this demo is based, it's going to be in a 3-node cluster. It will have Hadoop 2.7, Spark 1.6, built with Scala 2.10. We didn't deliberately build it with 2.11 because there is a known bug in sparkling water with one of the machine learning algorithms. And these node, the cluster of node, is running on the developer cloud. Thanks to the SDI team, it's all running in the ARM-based hardware on the developer cloud. And this all has been independently built and compiled on ARM and tested. So we're going to get data which is pretty much open from some of the cities. We're going to collect the open data that they have exposed, and then it is going to be stored in HDFS, and it will be read through Apache Spark and converted into Apache Spark RDD, and then H2O will read from there and convert it to H2O frame, and then we'll look at the H2O flow, the web UI, and we'll build a model and apply some machine learning algorithm onto it. Okay, so I got the Hadoop and Spark and sparkling water installed into it. So lack of time, I have also loaded the data into the HDFS. So let me go ahead and start the Spark. So what this has done is it has created one master node and two worker nodes. The Spark driver will be running on the master, and the executors will be running on the worker nodes. And now I'm creating the sparkling cell, which is a cell where you can put in your H2O commands. And while that is going on, I can show you the developer cloud instances that we are using. These are the nodes, Big Data 1, 2, and 3. And Spark also comes with a web UI to see the master and worker nodes. So this is the master, the web UI to see that. So you can see that there is one master and two worker. And by default, they get exposed through 8080, port 8080. And you can also, see the Spark jobs and how they are running, and that gets exposed through port 4040. And here you can see that the Spark is up and running, and the executors are up, and these are the different stages the job goes through. And this is the H2O flow web UI. It's still loading up. Okay. So you can see here, like I said, it provides an easy way for you to build models, and there's model menu there. Now you can select machine learning algorithms on it. So we'll go over the data set. So I'm selecting a data that New York City has exposed. New York City has these bikes that they have placed all around the city for the people to rent, and then they can drive. So this data has the information about people, what time they rent, how many miles they ride on the bike, how frequently they ride it, and how long they rent it for a day or a week. So we just imported that into H2O, and you can parse this file. When you do the parse, it kicks off jobs behind the scene, and that's run in the Spark. So you can see the job that progressed. And you can view the data getting parsed. This is the data that is parsed. And if you want to see actual data, you can click on the view data itself. And you can see here the date and time, and the trips that they had made in the last 24 hours. That's the total trips, and the miles traveled in a day, and how many people were renting it. So you can use this data, now go and create a model. To create a model, what we're going to do is we're going to first split the data into 80% and 20%. 80% is to train, and 20% is to test. So we split the data now into 80% and 20%. The whole data gets split into two sections, 80% of the data and 20% of the data. And now you can go and build a model. And you can choose an algorithm. I'm going to select generalized linear modeling. And for this model, now I'll say use the data, 80% data to train, and to validate, use the 20% data. So that builds the model. And you can actually save this model, and if you have new data, you can use the same model which is already trained, and you can use that to do the predictive analysis. So you can see the model, and it shows a graph also. And if you want to do the predictive analysis, you just click the predict, and you can select the model and click on predict. So we at the big data team, so we've been working on quite a lot of synthetic workloads and small workloads that comes with the micro benchmarking workloads that comes with the Hadoop. Now we are going into the next stage of looking at real world data and even benchmarking against it. So that also leads me to the next section. So we're going to talk about the benchmarks, why we need benchmark, what are the different types of benchmarks that's out there for big data. And we are going to go into each one of them and give an overview of them. And we worked on quite a lot of benchmarking last few weeks. And we will go over what those benchmarks are for and what kind of metrics they give out, and what are the issues that we have faced. And these are specific for ARM. So obviously, so we saw this demo, so we know that there's quite a lot of potential for big data. So there's a lot of interest, a lot of people talking about smart cities, and there's a lot of open data available. A lot of people are starting to combine data, and like in the previous demo, you could use multiple data sets and use Spark SQL and start combining and look at machine learning. So there is a lot of potential. So that also leads to that there are so much variety of data, right? There's different types of solutions that you can come up with the machine learning. But how do you benchmark between, how do you differentiate between a particular solution with another solution? So we definitely need some kind of benchmark from a hardware perspective and also from a software perspective. And also, big data, the data is growing in a very rapid phase, and the types of data that is also are very diverse. You have data, huge petabytes of data someplace sitting and you want to analyze. And you may have data coming from search engines, you want to index that. You may have data that is coming through as a streaming data. You may have data warehousing data where you may want to do a lot of reads and writes. You want to do filtering of data and things like that. And you may want to do machine learning. So there's quite a lot of data and it's growing. So it becomes more and more important on why we need benchmarking. So now With benchmarking, there are various types. You can have micro benchmarks that comes along with the Hadoop itself for sorting and grab and word count and terasort and things like that. There is also component benchmarks for each components that you can do, and application level benchmarks. So I'd like to ask Naresh to come over and explain over some of the benchmarks. He'll go give an overview and go in depth into each one of them.
Okay. We have actually big data team sit together and we have listed a couple of benchmarks. First thing is this is micro benchmarks. So this benchmarks actually metrics is like execution time and throughput resource utilization. So, and the Highbench, DFS-IO, and AmpLab, these are the three micro benchmarks. Workloads are like for Highbench, sort, word count, terasort, and page rank, k-means, base, classification, and index. And for DFS-IO, it's a generate and read, write, append, and remove the data for MapReduce jobs. AmpLab benchmarks workloads are like part of CALDA workloads. So we'll go for. So this micro benchmarks basically used for testing Hadoop, Hive, and TZZ stacks, software stacks. Next one is TPC benchmarks. We have like considered the three benchmarks: TPC-XHS, TPC-H, and TPC-DS. For these workloads are like HS generator. We'll go in detail these benchmarks later. Then data warehousing operations and decision supports. Like this, for these benchmarks, metrics are like performance, price, and energy. Like execution time and throughput are the for the TPC-H and TPC-DS benchmarks. The software stacks, Hadoop, Hive, and Pig. For these testing, you can use this. Next one is like synthetic benchmarks. Swim, GridMix, PigMix, MRBench. Most of these benchmarks it comes with Hadoop actually. When you install Hadoop, it will be in the examples of the Hadoop jar file. So big data bench is also a in the you'll get it when you install the Hadoop. This metrics is throughput, memory, and CPU. We can use it for the benchmarking this. And software stacks are like Hadoop and HBase, Impal. A lot of things will be covered in the big data bench actually. Hadoop benchmarks and test tool. Like as I told, like Hadoop distribution comes with a lot of benchmarks, number of benchmarks. Test DFS-IO, NNBench, MRBench, then Terragen, Terasort, TerraValidate. You can check the different benchmarks with the below commands actually. While running these benchmarks, you can use the time command so that the example snapshot will output will be like that, where you will get the matrix actually. This is a sample example. Okay, Terrasort, Terragen, Terrasort, and TerraValidate. Basically, Terragen generates the data set, and Terrasort runs on the input data. Validate will validate the generated data actually. Actually, we did run these benchmarks, and you can have a look into wiki page how to compile and configure and run these kind of benchmarks on ARM64 architecture. Highbench actually contains a 9 typical Hadoop and Spark workloads, and sort, word count, Terrasort, TestDFS.io, etc. And it uses actually zlib compression for input and output. There are actually lack of AR64 bits and lack of documentation how to configure, build, and run this benchmark actually. So you can have a look into our wiki page what we have created, how to do this stuff actually. TestDFS.io, it's a part of Hadoop MapReduce client job client. You will get this benchmark when you install the Hadoop on your system. So basically it tests the name node and data node, and it helps to discover the bottlenecks in your network. When you run this benchmark, you can use you can first write it and then read, followed by read. So this is how this benchmark will work actually. And the results are stored in the TestDFS.io results log file. You can use RES file for the to use a different file name or something like that. HiTestbench is like based on TPC-H and TPC-DS benchmark to experiment the Apache Hive on any data scale actually. It contains the data generator and a set of data queries. Test the basic Hive performance on large data sets. We did run this benchmark, and we have created a wiki page for the same. MapReduce benchmark. What it does is basically loops a small number of, like a small job number of times, and checks whether it runs, the job runs are very responsive or not, running efficiently on your cluster. Puts a focus on MapReduce layer as its impact of HDFS layer very limited. Okay. The test command is like to run the 50 small run, and the exemplary output is you can see. NNBench and NNBench without MapReduce. Load and testing a name node through continuous read, write, rename, and delete operations on small files. This does actually kind of a test. So if you run this benchmark, it will check whether your name node cluster is the sample command is as below, test command, and if you want to run the NNBench benchmark with reduce, you can use the option -reduce and maps. If you don't want to run, NNBench without MR, you can use, you can remove all those stuff actually. TPC is a TPC benchmark. TPC is, as I told, it's a one body, standard body. We tried to run the TPC HS benchmark, and we are currently facing some issues with configuration. We didn't run TPC H, DS, and TPC C benchmarks. We'll try to do it in upcoming days actually. DPCH focus on the ad hoc queries, and the TPCDS is the standard benchmark for decision support. TPCC is online transaction OLTP benchmark actually. TPCX HS benchmark. So X is for Express, and H is for Hadoop, and S is for sort. It comes as a kit, and it contains a script to execute the benchmark, and Java code to execute the benchmark load actually. So execution, this is how you need to do the execution actually. A valid run consists of 5 separate phases actually. So with all of their execution, the benchmark test consists of 2 runs, run with lower and run with higher TPCXHS performance metrics. And no configuration or tuning changes or rebooting of your system. This is not allowed in between while doing this benchmark actually. Okay, let's see the difference between TPC and spec models. TPC is actually a specification-based model. Spec model is a kit-based one. Here, actually, in TPC model, performance, price, energy in one benchmark. And here, in spec model, the performance and energy in a separate benchmarks. TPC is end-to-end, and a spec model is a server-centric. TPC model executes actually multiple tests. Spec model executes a single test at a time. TPC model follows the independent review, and spec model is a summary disclosure actually. TPC is a technology conference, and like spec model is a research group actually. Big bench, Ganesh, you want to cover this? Oops. Thank you.
Okay, Big Bench is a suite of benchmarking benchmarking tools. It actually borrows from various other benchmarking suite, including TPC, some of the micro benchmarking, and it takes some of the workloads from them, and it has added its own workload. So, right, and it is evolving quite a bit. It is worked by Cloudera and Intel, and there is a lot of academic interest in this. So this is evolving a lot. This is one of the main standards in big data benchmarking. Only thing is, it focuses mainly on structured data, less on unstructured data. So next is Spark Bench. Spark Bench is more specific to Apache Spark. we currently are working on it. We are having few issues in testing it, running the workloads. We were able to build it on ARM, but when we run example workloads, there is a kill signal that is getting called, and then it kills it. So we are still debugging it, trying to figure out how to do this. Obviously, there is a lack of documentation. There's a lack of documentation with many other benchmarks in regards to ARC64. So that's why we've been going through each benchmark, and we are trying to document everything and put it in the Linaro wiki. So we have links everywhere, so you could go and check it out in those as well. And grid mix, and it's a synthetic benchmark again, focused on MapReduce and HDFS performance. It has load job and sleep job. For the load job, it looks at the history logs and loads it. It uses Rumen for that. And sleep job is basically it invokes jobs and puts them into sleep. You can run them run this benchmarking in a stress mode, or you can do a replay of the previous one and check how it performs compared to the other. Or you can do a serial of benchmarks. Next is Pig Mix. This is in particular to Apache Pig. It's more of a data warehousing kind of a performance benchmark. This SWIM is another body which provides a benchmark focused on MapReduce as well. AmpLab is UC Berkeley created benchmarking suite. Now, it focuses more on data warehousing tools like Hive, Impala, or even Thais. It also focuses on data pipeline creation. So you can use that for Apache Spark benchmarking as well. Another suite of product is Big Data Benchmark. This is different from the Big Benchmark, and this focuses on sequential multi-threaded workloads. With that, these are the links and all the effort that we have put in running all these benchmarks and figuring out the issues. And some of the places we didn't have ARC bits, so we had to compile them and build the ARC bits. And you will have all the information in this, even the ARC bits, the links to them will all be in here. With that, this concludes the talk, so I'll open it up for questions, if any. Okay, we have the wiki page for the demo also, including how to build the Hadoop, native Hadoop, ODPi spec-based, and how to build Spark, H2O, sparkling water, and even how to run those demos. You can go and check out the wiki page for that as well. Thank you.